Yes, so straight from the horse's mouth. I'm going to provide you an overview of the monitoring plan for Northern Lights and how this contributes to ensure operations safety. Yes. If you don't know what Northern Lights is a transport and storage project, part of the Longship full value chain captures the transport and storage project sorry, I'm thinking Norwegian today, that the Norwegian government desired and got through FID in 2020. After that, Northern Lights became actually the operator and a different company, a JV, equally owned by three owners, Equinor, Shell, and TotalEnergies, which I am glad to acknowledge in the audience today. And what we're doing, we are injecting in a sloping saline aquifer in a Jurassic unit called the Danling Group. And my Attica. Down here, we are located 100 kilometers from the Norwegian coastline, and we are injecting at a depth of 2,700 meters plus minus. We have a secondary storage unit which is below the Statfjord group. It's also slightly older, and it's in pressure communication is hydrostatic, same as the primary storage unit. Our primary seal is the wonderful Drake Formation. It's marine shales. It holds a pressure differential from the overburden, which is produced by the very big and nice neighbors, the troll fields. Although the main producer of the troll fields is even above that, and it's absolutely not part of our operations. Phase 1, as mentioned, was sanctioned in 2020 with a target injection rate of 1.5 megaton per year for 25 years, with one injection well, a sidetrack to this well bore, and a contingent well in case of stops. We are operating since August last year in the phase 1 part, but last year was fantastic. We also reached FID, so final investment decision for the expansion, which is phase 2, where we're going to increase the number of wells and increase the injection rate. And we're planning to start it in 2028. So how we monitor this storage complex and why? The why is being discussed at length before. We need to confirm containment and conformance. So we need to prove that we are storing safely in the target hydraulic unit. But we need it as a tool for communication and compliance. So we need to demonstrate that we are doing so to investors, customers, the public opinion, and the authorities. Plus, it's a source of information. With the information gathered from the monitoring, we can adjust and optimize CO2 capacity, injection scheme, and daily operations. The how is also kind of the structure of my talk. We are using active 4D seismic monitoring to assess the location of the CO2 in the subsurface, find the migration path, and detect that it's not going above the cap rock. We are having a already very nicely illustrated passive seismic monitoring plan to distinguish between natural or potentially induced seismicity events. And we have the in-well monitoring, which is, of course, looking at pressure, temperatures, and it's giving injection well performance, the pressure development near well, and also in the storage complex. What I haven't talked about yet is the who, and I'll mention that along the way, and the when. So active monitoring is happening at intervals, which is in not in time, but in injected volumes. Passive seismic monitoring and in-well monitoring are occurring real time, and they are continuous. Some in-well monitoring derivatives in a way, or activities are also happening discretely. And I'll come back to that. So active seismic, we can't do this without a baseline. So before the operations, already in 2022, we acquired 600 kilometers of high-quality seismic data, 3D. And we went for this solution to make it as much repeatable as possible, to cover all those areas of interest, not necessarily concern, but interest. We want to get the best possible imaging of the storage complex, also to understand it, to see if there are heterogeneities we could not see with the legacy seismic, and to be able to make it repeatable and good over time. We also had a positive positive view of the overburden. I'm not sure that, where we actually gather additional information. So to set a snapshot of the situation before injection started, this was acquired in 22. And it's wide extent, again, to cover the area of interest, but also to cover the worst case scenario. The idea was, and this is the who, thanks to the reservoir engineers that had the input on the dynamic model and on the plume development over time. We had, and because of the geology, because we are sloping to the south, so the plume will move to the north, we know we're going to move towards the northern part of the northern border. So we want to cover that to assess how the CO2 will move towards the point of interest. So first came the dynamic modeling, and then the reservoir engineers and the geophysicists sat down and came with a location of the baseline. Then the geophysicist went into really detailed work to find out what was the best way of moving the boat north and south, this is offshore, to do it in the smartest way possible and ensure that we get repeatability. And I'm not super qualified to mention this, but we have the possibility of extending, of course, northwards and southwards, should this become needed, or to keep the monitoring, the repeats within this area. So this caters for future also adjustments of the 4D seismic, should it become necessary. And as mentioned, we have such a good quality data that we could make inference about the overburden and even the surface, the seabed. So the high resolution processing helped finding out features on the seabed that are supporting while planning for the next wells. So this is a comparison between the available data. Sorry, this is the available data and this is the new one. So some feature that were just maybe visible becomes a lot more evident, and we have a better tool to place wells in a safe way. So these are pockmarks, and they are due to fluid movements after the last ice age. So nothing to do with any industrial operations in the Norwegian continental shelf. But we want to avoid them when we place the well. So knowing where they are, it's top. And passive, it was mentioned before. Thank you very much, Bettina. So the reason is, of course, detect any irregularities, detect any events that could maybe be induced. And this is for public acceptability and the project reputation, of course. Plus understanding if we are causing stress changes in the reservoir and the caprock. Well, this is just a repetition. There is quite a bit of seismic events in the area. We are located a bit further out of the main area, which is closer to the coastline. And the whom, in this case, is the HNet, or the Seismological Network, which is a research and technological consortium, which was joined by Northern Lights to improve the understanding and monitoring of earthquake and seismic hazard. And this was an impulse from one of our colleagues from TotalEnergies, a true geophysicist. So yes, that's true, depth control. Currently, our sensors are mostly on land. However, for phase 2, for the expansion, we are working really hard, I might say, to be able to interrogate, to get the data from our DCFO, our fiber optics, the communication cables, which are already on seabed and link Northern Lights to Oseberg platform, where the wells are operated from, and also to the wells. The ambition is to install fiber optics in the wells. The challenge is that they are offshore wells and they are from subsea templates. So the lower completion is still really challenging to have fiber optics. We can have it in the upper completion. We're working on it. And why? So how are we using this data? So first of all, we are having dashboards, seeing is there any event that can be located with the present uncertainty, of course, within our area, yes or no? And if so, what it is. Is it a small one, like a magnitude less than 2? Then we write it down. If it's between 2 and 4, then we distinguish between single events or a cluster. And then we initiate the response plan. If it's a 4, it's no matter if it's a single or cluster, then it's when we reduce injection and we start maybe remedial monitoring and additional measures. I forgot to say that I'm talking about the plan monitoring. Of course, in case of irregularities, we have also the triggered monitoring. It depends on what we observe. So in a way, it's a cycle. We observe, not just from the seismicity, after the 4D monitoring. If we see irregularity, then we take action and we close the circle. So in terms of communication, I'm here talking to in international conferences. We have the HNet Consortium public dashboard. We are trying to publish in peer-reviewed science papers so that things are communicated the right way. And last but not least, not mentioned today yet, in-well monitoring. So I'll start with the who. In this case, it's Equinor Courtesy in this plot I'm showing. It's a screenshot from one of the dashboards that we are using for actively following up a well. There are several of these, and wells operated by Oseberg have similar ones with alarms. So when things are not behaving, there is a high alarm or a low alarm, depends on the parameter, and then a high alarm. So warning, and then critical values, and potentially even emergency shut of the well. But this is a case of actually a plan shut-in, and we see the curves at all times. So it's difficult to read, but we had downhole pressure, downhole temperature increases when we stop injecting because the CO2 is cold. When we stop injecting CO2, the reservoir heat warms up the well. And this is funny. These blicks are the automatic choke control. So the well is choked automatically, and sometimes it's small adjustments happening. And then the choke opening goes down to 0, and the flow rate goes down to 0. So business as usual. And yeah, but then how are we using this information? This is the real continuous information. But when we have, I'm making an example here, when we have a startup, then we can perform a step rate test. And this is, again, not my field of expertise, but what we can do is to observe what happens in a new case, the red lines, versus previous observation. And the change in inclination of the lines gives us information as of are we injecting matrix, are we creating fractures. So by comparing new with old, the slope change and the baseline or the actual values, we can make inference about what's going on in the reservoir. So far, so good. That's how much I can tell you. And yeah, the WHO, of course, injectivity, injection rate by delta P. So far, so good. And my colleagues, the reservoir engineers, are quite happy about that. I got permission to use the picture. This was actually the day of the startup, so they were super excited. So eventually, key messages. I hope I managed to convey that we are a JV that can transport and store CO2 geologically as a service. And because of the setup of Longship, we're happy to be quoted because we want others to succeed. I know it's counterintuitive when we are also in commercial operations, but that's how Northern Lights was set up for. And we monitor to enable risk mitigation, of course, but also safe operation, day-to-day decisions, and verification of the conformance, of the containment, and as a communication tool. So the three pillars: active seismic monitoring, 4D baseline is acquired, totally fulfilling its operational objectives, and it's going to be used for comparing when we reach an adequate injection volumes. The passive seismic monitoring, we have our dedicated network of sensors, we have a response plan, we are working to increase with fiber optics, and then the in-well monitoring, day-to-day, and really a lot of information just from the wells. So, yep, ready for the next customers.
Thank you, Renata.